Some exercise. People, please remember that when trying to identify if any two structures represent any type of isomerism in between them, the very first thing that you need to do is to check their condensed formulas, because if the compounds have different condensed formulas, there's no way of having any type of isomerism. And it's also important to see that even though some compounds do have the very same condensed formula, if the arrangement of the atoms in their structures is the very same, they too, once again, are not showing any type of isomerism. So, let's start with this first pair of compounds. I'm going to try to make it easier for all of you now that we have already studied the aromatic compounds naming system. I see that I have this complex ether hanging as a branch from this benzene ring, and that to the other side I have a methyl. And if I check my structure here, I have the very same thing. So then I don't really need this time to check the condensed formulas, because they for sure have the same condensed formulas. Anyhow, what's important to see is that the positions of the substituents in these di-substituted benzene rings are different. You have a one substituent here, which will be the one responsible for giving the name to this aromatic compound, position 2, 3, and 4. If I move on to this one, this is going to be carbon atom 1, because you have here the most complex substituent, carbon 1, 2, and 3. Also remember that when having a di-substituted benzene rings, we do not name them by giving the numbers of the positions, but instead by using the words ortho, meta, or para. Ortho meaning that the substituents are in position 1 and 2. Meta, that the substituents are in position 1 and 3. And para, that the substituents are located in opposite positions. So, by using the names for these two compounds, this one is the para methyl anisole. Well, on this side I have a 1, 2, 3 ortho meta. This is a meta methyl anisole. They are the same compounds, methyl anisole. What's the difference between them? The difference is the position of the substituents, 1, 3, 1, 4. So what type of isomerism do I have here? We have a position type of isomer. Exercise 2. We have alkenes on both sides, but let's check the condensed formulas. I have 1, 2, 3, 4, 5, 6, 7 carbon atoms in my alkene. If this is an alkene, the number of hydrogens that I must have is 7 by 2, which makes 14. I only have one double bond. On this side, I have 1, 2, 3, 4, 5, 6 carbon atoms. 6 by 2, I only have 12 hydrogens in this alkene. The condensed formulas are different, so then these two structures are representing different compounds. No isomerism is possible. The following pair of compounds, condensed formula, 1, 2, 3, 4, 5 carbon atoms, 5 carbon atoms. Where am I writing? Sorry. 5 carbon atoms, 1 oxygen, 3, 6, 7, 8, 9, 10 hydrogens, H10. Let's make the same account for the carbons, hydrogens, and oxygens in this structure. 1, 2, 3, 4, 5. I've also got 5 carbon atoms, 3, 5, 7, and 3, 10 hydrogens, and 1 oxygen. So my condensed formulas are the very same. In this case, I can identify 2 different types of isomerism. What really calls out my attention is the functional groups that I see. On this side, I see an aldehyde. Well, on this side, I see a ketone, because my compounds have the very same condensed formula, but a different arrangement of the elements along the structure. This is showing a functional group type of isomerism. But as I was saying, at the very same time, if I check the continuous hydrocarbon chain, in this case I have 1, 2, 3, 4 carbon atoms in my parental strand of this butanol with a methyl branch, while on this side I have a continuous 1, 2, 3, 4, 5 parental strand. And so therefore this is also representing a chain type of isomerism. If I move on to the last pair of compounds, how many carbon atoms do I have for this structure? 1, 2, 3, 4, C4. It's also a double bonded structure, an alkene, so 4 by 2, I must have 8 hydrogens, 3, 4, 5, and 3, 8 hydrogens in this condensed formula. If I do the same thing for this one, 1, 2, 3, 4, C4, H, 3, 4, 5, and 3, H hydrogens. I have the very same condensed formulas. Both of my formulas have a continuous parental strand of 4 carbon atoms. But remember that when having double bonds, the chances for the compounds to be showing geometric isomerism arises. I analyze that in this side, my complex substituents, the CH3 and the CH3 for these carbon atoms, are located into opposing sites. And so therefore, this is the trans isomer. Well, the one on this side, because the substituents of the carbons bonded by the double bond are located towards the same location, this is the cis isomer. And so what type of isomerism do we have in this pair of compounds? We have geometric isomerism. And that's it for this other compound.